Today, we will talk about bioprinting technology. Discuss the potential impact of bioprinting technology in organ transplantation, tissue engineering, and medical research. 1. Inkjet bioprinting. Inkjet bioprinting is a popular technique in tissue engineering that utilizes inkjet printer principles. Employing thermal or piezoelectric actuation, droplets of bioink containing cells and biomaterials are precisely deposited onto a substrate. The process is non-contact, which can reduce cell damage. It's capable of high-speed deposition and is relatively inexpensive. However, it often handles low-viscosity materials and may face clogging issues. As in 2D inkjet printing, the droplets coalesce and solidified form desired structures. By layering, it's possible to create complex 3D tissue constructs. The technology's resolution and speed make it promising for various biomedical applications. 2. Laser-assisted bioprinting. Laser-assisted bioprinting, LAB, is an advanced technique rooted in the principles of laser-induced forward transfer. The process involves a pulsed laser beam focusing onto a ribbon layer, which subsequently generates a high-pressure bubble, propelling a droplet of bioink onto a receiving substrate or biopaper. The bioink can contain cells, proteins, and other biological materials. One of LAB's advantages is its high spatial resolution and cell viability, offering precise placement of cells. It doesn't involve nozzles, thereby eliminating clogging issues common in other bioprinting methods. LAB is especially suitable for creating complex multicellular structures, making it invaluable for tissue engineering and regenerative medicine applications. 3. Extrusion-based bioprinting. Extrusion-based bioprinting is a widely used method that employs a continuous dispensing mechanism to deposit bioink, a viscous material containing cells and biological components, layer by layer to fabricate 3D structures. This technique uses either pneumatic or mechanical systems, like a syringe pump, to extrude the bioink through a nozzle. The size and shape of the outputted structure can be controlled by adjusting parameters like nozzle diameter, extrusion rate, and print speed. Advantages include the ability to handle high cell density and various biomaterial viscosities. However, mechanical stresses during extrusion can impact cell viability. The technique is widely adopted for its versatility in creating vascularized tissues, organs, and other complex biological constructs. 4. Microvalve-based bioprinting. Microvalve-based bioprinting employs microvalves, typically solenoid valves, to control and deposit droplets of bioink onto a substrate in a layer-by-layer fashion to construct 3D tissue structures. The process involves the opening and closing of the microvalve, releasing precise volumes of bioink. The deposition frequency and droplet size can be adjusted to control the resolution and overall architecture of the printed tissue. An advantage of microvalve-based bioprinting is its ability to dispense a wide range of bioink viscosities while ensuring high cell viability. Additionally, it offers repeatability and scalability, making it suitable for producing tissues with controlled cell densities and patterns. The nozzle-free nature also reduces clogging issues. 5. Stereolithography, SLA bioprinting. Stereolithography, SLA, bioprinting is a light-based 3D printing method that utilizes UV light to selectively cure photosensitive bioinks in a layer-by-layer approach to construct three-dimensional biological structures. In this process, a vat of liquid photosensitive resin, which can contain cells and other bioactive molecules, is exposed to a directed UV light source. Where the UV light strikes the resin, it cures or solidifies. Once a layer is cured, the build platform moves, and the next layer is cured atop the previous one. SLA's main advantages include high resolution and smooth surface finish of printed structures. However, potential challenges include ensuring cell viability due to UV exposure and achieving appropriate mechanical properties for biological applications. 6. Digital light processing. Digital light processing, DLP, bioprinting is a variation of light-based 3D printing techniques. Instead of using a directive UV light as in stereolithography, DLP employs a digital light projector to flash UV images onto a vat of photosensitive bioink. Each flash cures an entire layer in one go, rather than point by point or line by line, making the process faster. The precision of DLP bioprinting is determined by the projector's resolution, allowing for intricate structures to be printed. This technique has the advantage of high-speed fabrication with a smoother surface finish. 7. Two-photon polymerization. Two-photon polymerization, 2PP, is a high-resolution bioprinting technique based on the principle of two-photon absorption. In this method, a focused near-infrared (NIR) laser beam is utilized to induce localized polymerization in photosensitive materials. Remarkably, polymerization occurs only at the focal point of the laser, allowing for submicron resolution in 3 dimensions. 2PP's major advantage lies in its ability to produce intricate structures with unparalleled precision. Since the polymerization process is highly localized, it's possible to fabricate complex and detailed architectures, which are often unachievable with other bioprinting techniques. 8. Spheroid-based bioprinting. Spheroid-based bioprinting is an approach that uses cellular spheroids as building blocks to construct 3D tissue structures. Spheroids are tiny, self-assembled aggregates of cells that can mimic the characteristics of tissues more closely than individual cells. During the bioprinting process, these spheroids are strategically positioned to promote fusion and subsequent tissue formation. The primary advantage of spheroid-based bioprinting is the inherent ability of spheroids to self-assemble and create natural tissue structures without relying solely on external scaffold materials. This method also tends to maintain higher cell viability, as spheroids can better preserve the cellular microenvironment. 9. Droplet-based bioprinting. Droplet-based bioprinting, often seen as a subset of inkjet bioprinting, revolves around the deposition of cell-laden droplets to create 3D tissue structures. This method employs either thermal or piezoelectric mechanisms to eject discrete droplets from a nozzle onto a substrate. The primary advantage of droplet-based bioprinting is its ability to control the number of cells in each droplet, allowing for precise cellular arrangements and density. The droplets can merge or coalesce to form continuous structures, and the process is gentle enough to maintain high cell viability. 10. Magnetic levitational bioprinting. Magnetic levitational bioprinting leverages the principles of magnetism to position and manipulate cells and other biological materials in a 3D space. In this technique, cells are first magnetized by incubating them with magnetic nanoparticles. Once magnetized, these cells can be levitated and organized into desired patterns and structures using external magnetic fields. The key advantage of this method is that it allows for scaffold-free and nozzle-free bioprinting. This reduces mechanical stress on cells and avoids the clogging issues inherent to nozzle-based methods. The technique can precisely arrange multiple cell types, enabling the creation of complex multicellular structures. What do you think of our video? Let me know in the comment section below. Before you go, please hit the like button and subscribe to my channel. Thanks for watching.